And next we will have our second speaker. Our second speaker is Axel Sauer from Max Planck Institute for Intelligent Systems in Tübingen.
Yes, hi. You can hear me?
Yeah,
cool.
Sure.
All right, awesome. Hi, everyone. Yeah, I'm from Uni Tübingen, and I'm going to talk about counterfactual generative networks. So I'm going to share my screen in a second.
Sure.
And here we go. Cool. Okay, so let's go. So first off, these four images, if you look at them, like those are the motivational examples I'm going to use throughout the talk. And so if you look at them, usually what you see in image data sets, if your task then is on those images to classify if this image shows a cow or a camel, then you would get images like these on the right. So you do have the cow on green pastures, and you do have a camel in the desert. But of course, like those images on the left here, they also do exist. I mean, I can depict them here. But usually, like just a model trained on this IID data, then would most probably it would fail classifying those correctly. And also, I mean, what about an image like this? So a classifier should still confidently assign a label cow to this image. So, and in a nutshell, the motivation of our work here is if we have a real image like this one, this ostrich, a normal classifier would tell us that's an ostrich. But what we would like to have is a classifier with different heads that classifies different factors of variation in this image. So this is an ostrich shape, texture, and background. And if we generate this like funny looking counterfactual image where we switch out the texture and the background, but just leave the shape unchanged, then a normal classifier would most likely give us anything, maybe focuses mainly on texture, then it would tell us it's a strawberry. And again, in this case, we would like to have a classifier that tells us that's an ostrich shape, strawberry texture, and a diving background. And like this per se is not that interesting. I mean, academically interesting maybe, but what we then would like to have is we know that maybe we want to factor out the background in this model. Then we could simply just disregard this classifier prediction and just focus on those two, if we do know that background might be a spurious signal. So, and the counterfactual image that I showed is actually one that we generate like in the following, but like how to generate these counterfactual images is not trivial, because like if you have this data set here, where you do have a color bias on the standard MNIST, and then you train like something like a beta VAE, a disentangled VAE, then the latent space, if you walk through the latent space, and like if this latent space is only two-dimensional, the latent space looks like this. So you do have like only like red zeros and yellow eights. So everything you saw in the data set, and like it's not very surprising since this is maximum likelihood modeling, you wouldn't expect that this generates just out of the box counterfactual images. So it can never generate like a yellow zero, for example. I mean, it's barely there, but like a blue zero is basically impossible in this case. So what we also do is like this is a fairly common data set nowadays. Like a few works use this already. We basically amplify the difficulty also by switching out the background and then doing the same thing, but now, or like also this is then highly correlated with the label. And then we can switch out the colors for textures, so making it even harder. And now the common assumption usually is also in the models you've seen in the previous work, usually you do have like a single decoder that is just a single neural network that just models all the image generation in one big complex function. And this is also what is assumed in this prior work here, and like all those errors are subsumed in one big neural network. And what we do now is that we take inspiration from causality literature of structural causal models, and then train separate neural networks to represent different independent mechanisms, and what this means in a second. And this structural causal model is defined as the structural assignments. And all of those together then define this unique entailed distribution. And now what means intervention in this case is that we replace one or more structural assignments, and the entailed intervention distribution then changes to this PS C do, SK equals A. And A in this case So what we're talking about is a distribution that changes basically the input to these independent mechanisms. So if we generate a counterfactual image, or if we want to generate this, then we basically fix noise and randomly draw A. And in this case, A would be the label. So imagine we generate an image of a cow on the green pasture, and then we say, how would this image look like with a different background? So we do have like one mechanism generating the cow and one generating the background. And then we say, we change the input to the background mechanism, and then we can switch this out. And the task in this case would be if we do have, in this case, a background classifier, the background classifier is supposed to classify the counterfactual label, so the one we switch out and actually know what it is. And then we can have like several classifiers that then basically classify those different factors of variation that we do have modeled. And how this concretely looks like is that we built on GANs, and we do have several generative networks here. And one of them, as I was alluding to, is we do have the shape, we do have the texture, and we do have the background, and all together then form the final image. So in this case, it's a 0 with this background that's always in the background. With the texture always in the background, and the foreground is always this texture for a 0. So we can simply just train this with an adversarial loss. But since we do model, like this is a structured causal model, we do, by construction, we are able to simply now, if this is trained, switch out the input. So we provide, for example, this network here, a different label, and then we can simply just generate a different background. And the reason why this works is that we do have here like this bottleneck where we do compose the final image, and this is just like a fixed function, like it's alpha masking. So this is a fairly strong bias, which then allows us to only like train with an adversarial loss and learn those different signals. And so now if we do this on these different data sets that we proposed also, we then can generate counterfactual images. And you see that like those are the generated ones on the right. Those look like fairly convincing, I would say, especially like the texture ones, like considering the foreground texture, like you only see those on the small shapes here, and it's still like the texture mechanism runs like a fairly good signal of generating this texture. There's like some tricks how to actually then get this only to non-texture. So we do this with a architectural bias, like there's a specific layer, but I won't go into detail on this, but it's in minor detail here. So I know what we set out to do is that we would like to basically have a robust mechanism, a trained classifier. So in this case, we know that we obviously like the shape would be the causal signal, so we want to disregard everything else. So what we do is we generate an image, then randomize the texture and the background, and then train on the original data plus this CGN is counterfactual generative network data. And then we can see that it's focused on the right here for wildcard damage, since this is the hardest one. All the other approaches mostly fail. But here it's still possible in a test setting where everything is randomized and training is like 100% correlated, it's still able to get a fairly good test accuracy. The other one that's still okay-ish is like the IRM, which probably is familiar to some of you. It's the invariant risk minimization, where you do have different environments with different amounts of correlation. So we vary this from 90% to 100%. We do have 5 environments, and then IRM finds the most causal, like the most stable signal is supposed to be the causal one. So this is also how this, if you increase the amount of environments, which is kind of fairly impossible in most settings, then this still works reasonably well. So then you might say, of course, in this setting, like the IRM assumption is much more general. Like you do, like you just have several environments. You don't tell IRM that this is supposedly the causal signal. The thing is, so we can also just drop the assumption that we say shape is the causal signal. We can also just go with the IRM assumption. We do have different environments of correlation. then we train only on this 100% data set with and generate data, counterfactual data, and then train different classifiers. So a shape classifier, a foreground classifier, and a background classifier. And then we see that shape classifier is the most stable one, whereas foreground and background varies across environments, which also then indicates, without us knowing which one the causal signal is, that shape must be the causal one because it's stable across environments. And now onto the cool looking images that we then finally can generate. Like we also extend this to work on ImageNet. And we make use of like different pre-trained backbones and different biases in the form of a detection, like salient object detection network. And then we basically put this together and to have like a normal conditional GAN that is supervising via a reconstruction loss. And we do have different losses also here. But so the most important thing is that we basically do the same thing as in the MNIST example, and then can generate like disentangle those mechanisms, and then again can pull those mechanisms apart and then change the input or the conditional input of each subnetwork. So we then can generate those cool images here, where we can just switch out the shape or just generate a red wine class and switch out the shape texture for spaghetti and the background for a baseball field. And this works also for all ImageNet classes. I mean, here I'm showing the ones that work really well. This, of course, is very dependent on the initial backbone that we use. So in this case, we did use this big GAN backbone, so the best that was currently available in terms of GAN. So obviously, like the classes that work well in big GAN do work well in our setting then as well. But in classes where big GAN fails, this also doesn't work as well. So it's still dependent on the quality of the backbone you start with. So these are the outputs of each mechanism during training. And so the first one is basically, or the 1.1 is a mask, so black and white image here for different classes. And the first one is the input or the direct output of the big GAN backbone before we feed it through the salient object detection network. So you see that what it's learning is to make the background very bland and the contrast to the object very high, which basically makes it very easy for the salient object detection network to generate a proper mask. And you see that over the course of training, for example, in the mask, the big GAN backbone is not perfect. Like we start out with an elephant with 8 legs, but over the course of training, like we do learn somewhat of a class shape prior, you could say, where you do have fewer legs. I mean, now it's only looks like 3, and there's another one coming in. But at least you get rid of some of the artifacts, interestingly, which we didn't expect at first. In the foreground map, you see that gradually over the course of training, the background is morphing into object texture for all these classes. And for the background, you see that first you do have the full object. So we do start out with the pre-trained big GAN backbone, as I mentioned. And then over the course of training, this backbone learns to basically unlearn the generation of an object and only leaves the background intact. And at the end, we again want to form this full image, which is like the composite image as we had it before. And also again, here we do some experiment with classifiers where we do show that we can increase the so-called shape bias in those different heads. So shape bias is something where you can measure on specific validation sets how strongly your classifier bases his decision on shape or texture. And we do see that for the shape head, so we do have like 3 heads, shape, text, texture, and background. And the shape head increases in shape bias, whereas the texture head actually decreases. So exactly what we want, because usually the texture bias is around, like normally trained on ImageNet at 21%, but texture here texture is lower, so the texture bias increases. And we can do all this without losing too much of accuracy. So we can kind of now steer the decision of each classifier towards a direction we want to have. So it's working here. And here we also have a different data set, which is like a subset of ImageNet and also from prior work, where they do basically they do the same thing we did, but manually on images and crop them out and paste them on different backgrounds to measure how much the classifier bases his decision on this background. And so you can see that usually it's around like 7% or 10%, depending on what you train it on. And if you train on this artificial generated data set, you do lose lots of accuracy, but you close this background gap. And we show that we're somewhere in between, basically. So we don't lose that much accuracy, only a little bit, but we do still close the background gap. So as we set out to do, like there's still like a remaining background gap, and we kind of attribute this to still the images not being perfect, obviously. Like we still do have a domain shift between the generated images and the image and images. All right, I think I'm right on time. Thank you. I'm happy to take questions.
Okay. Thank you, Axel. Maybe we can have one questions from the audience. Is there any questions? If you have one, you can just unmute yourself and or use the chat box. Okay, if there's no questions from the audience, maybe you can contact Axel offline. Yeah. Okay, thank you again. Thank you. Thanks for the presentation.